Hi everyone, welcome to trigonometry. Here we go, we're going to start with section 5.1. And so what I'm going to do is I'm going to put up some notes, I'll talk about them, and then I'm going to pause the video, put up some new notes and talk about them. It's going to be really fun. These will probably come in a couple of video chunks because YouTube is not liking big videos. So here we go. We're talking today about angles, and I don't know if you can read that. It might be behind my great white glare blob there. So I'll try to remember not to put stuff right there because it looks bad. Anyway, an angle is formed by two rays that emanate from something called a vertex. That's this point right here. You have what's called an initial and a terminal side. Now what an angle is it's a measurement of rotation. Okay, so it's a little different from pulling out a ruler and measuring. That's why you had a protractor once upon a time to measure angles with. Now, it's going to be important for us that we know the direction matters. Counterclockwise rotation will always be a positive angle, and clockwise will be a negative angle. And we'll see why here in just a second. But basically, direction matters because, let's face it, if you get into your car and you start driving, you need to go the right way. If you are in your garage and you are supposed to be backing up and you accidentally put it in drive, that would not be good. So direction matters, positive and negative. All right, so the reason that counterclockwise gets to be positive is because of what we're going to call standard form. An angle is in standard form if its vertex is at the origin and its initial side is on the positive x-axis. So the reason we want counterclockwise to be positive is because if you look at this angle that I drew here, by going counterclockwise, that brings that angle up into the first quadrant. And so that's a good seems to me to be a good reason to call it a positive angle. We have some kinds of angles here that I've listed. Hopefully you're familiar with all these. Acute is between 0 and 90. A right angle is 90 degrees. An obtuse angle is between 90 and 180 degrees. Straight angles are 180 degrees. And one full revolution is 360 degrees. Now you might be asking yourself, why 360? Why couldn't they have picked a nice normal number? I don't know. I really don't. I have some vague memory kicking around in my head that it's due to the ancient Egyptians. Google it. Could be an interesting learning experience. So anyway, these are our basic angles. We know that complementary angles, which I've not put on the board and I'm not going to, complementary angles are two angles that add up to 90 degrees, and supplementary angles are two angles that add up to 180 degrees. All right, so we're going to pause for just a second while I rewrite my board, and then we'll continue. All right, here's our next board. We're going to talk now about coterminal angles. This board won't take too long, and then we'll be ready to move on to another one. Coterminal angles are angles that end up at the exact same place. So you can see I have a picture down here of an angle. We'll come to this in just a second. 360 degrees is going to be our magic number here, or in just a little bit, 2 pi when we get to radians. And so that's something that we'll talk about. But for now, let's look at my angle here. So I have an initial side on the x-axis, just like we normally would. And you can see my terminal side up here in quadrant 1, or at least hopefully you can. So the idea is simple. There's nothing limiting us on how many times we can go around the circle. And so what that means is if I start where my initial side should be and swing all the way around and still end up at that same place, this is an angle that stops in the exact same place. It is called a coterminal angle because it stops in the same place. So what we get is as an example is this. Because it's one full extra revolution, let's pretend my angle was 30 degrees. I take 30, if I add 360 degrees, I get 390 degrees. That's the one I just drew. Okay, I started and I went the same direction, positive direction. I went one whole revolution, there's that 360 degrees, and then there's the extra 30. Together it makes 390. Now, you could go backwards. Okay, I didn't draw it here, but pretend for a second I had spun this around the other direction. If I had, I could still get back to this, and it would be the same as 30 degrees minus 360, giving us an angle of negative 330 degrees. So you can always find coterminal angles. You're just going to add or subtract 360, and you can do it as many times as you want. You can add 20 times if you really want. I won't ask you for that many, but you could. Okay, next board. So now we're going to talk about radians. You'll notice I didn't take anywhere near the whole board here because the next bit of my notes is needs more space than that. So anyway, radians. A radian is defined to be the angle that is subtended by an arc that matches the radius. Okay, a lot of big words there. An arc subtends the angle. It's just the bit of the circle at the end of my angle. That's what it means to subtend. And so what I have here is I have a circle with radius 1, and I've marked off what should be a length of 1 unit on my circle. Those two things match. The angle then is one radian. So you'll notice I marked out, going around here, some really important values. Now, we're hopefully all familiar with the degrees. 0, 90, 180, 270 is the one that's straight down, if you wrap your angle all the way around to there. And then all the way back to 360 degrees. We're probably pretty good at that because, we get the whole 90-degree thing. But I have here the radian measures that match up with those. And so we have those, and I would really highly recommend start to figure out at least these radian measures. It's going to be really useful for you as you go forward and try and figure out, how to do this trigonometry thing if you know what these are. So we have 0 radians here at the beginning. Up at the top is pi over 2, and out to the left is pi. The bottom is 3 pi over 2, and you get back to 2 pi. And the 2 pi is not a coincidence. Okay, it's actually coming out of the ancient Greeks. If you remember, they found this weird number pi that was equal to the circumference of a circle divided by the diameter. Well, another way to talk about circumference is in terms of radius. So circumference is 2 pi times the radius. And if your radius is 1, guess what? Your circumference divided by 1 is still just 2 pi. So that's where that number is actually coming from. It's that distance around my circle with radius 1. How about that? And so your angle going all the way around, and this is going to be a big magical number, is 2 pi. And that's going to be equal to 360 degrees. What we really want to focus in on, though, right now, and for my next board, is this right here. That pi and 180 degrees are exactly the same thing. All right, we're back. Next board. So now we want to talk about going back and forth between radians and degrees. Couple of good reasons. One, there are some things that we can only do if the angle is in radians, and we'll see some of those here in just a little bit. But almost more importantly is that some of you, and by some I mean probably most of you, are going to be a lot better at thinking about angles in terms of degrees. So for instance, if I give you an angle like 5 pi over 6, you're going to be like, what does that even look like? Well, the good news is we're going to switch it to degrees, and then you can kind of get an idea of what it looks like. So here's what we're working with. Remember on the last board I said that the key was that pi and 180 degrees are exactly the same thing. And so hopefully we can see that. I think you can. So what we're doing is we're doing a unit conversion to switch between the two. So since I'm going to start with radians here, and here's my example, 5 pi over 6 radians, I'm going to put the pi radians on the bottom because that will allow me to cancel the units. Now, I didn't write radians here, and it's important to note if we don't write the units, it's always radians. So anyway, the radians disappear, and also really nice, so do the pi's. Right? One's on the top and one's on the bottom, so they go away. If you do your fraction multiplication here, you end up with 150, and now it's in degrees. The flip side then is degrees to radians. We're going to use the same fraction, we're just going to turn it upside down. So this time I want to get rid of degrees, so I'm going to put my 180 degrees on the bottom. So for example, I have 210 degrees here, multiply by pi over 180. The degrees cancel, I'm left with radians, but remember, we don't write the units, it's always radians. So if you reduce this fraction, you get 7 pi over 6, and we really like the pi. Please don't get rid of the pi, just leave it there. That's our answer. We don't want to multiply that out. All right, moving on. Okay, finally, this section of the book concludes with some formulas that we use to work with spinning things. The important thing that we should know first, anytime we have an angle in these formulas, they have to be in radians. And yes, you have a math teacher who is absolutely mean enough to give it to you in degrees when you should be using radians. So let's start with arc length. Arc length is just a piece of a circle, okay? Or, I guess if you spin around a lot of times, it's tracing that circle over and over and over again. so S is equal to r theta, S is arc length, r is the radius, theta has to be in radians. So for example, I gave us a radius of 10 and an angle of 30 degrees. I had to first change 30 degrees to radians, so I multiplied by my pi over 180, just like on the last board, gave me pi over 6. Now I can just do 10 times pi over 6, right? R times theta. When I do that, I get 5 pi over 3. The other two formulas that we have here at the end of the chapter, and of course, you will be allowed your book on that next test, so I don't need to put these on a note card. But anyway, we have linear and angular velocity. For linear velocity, it's s over t, arc length divided by time. For angular velocity, it's theta over t. It's an angle over time. And so what we have, first of all, with linear velocity, it sounds linear, like a line, but what we're really talking about is velocity along a path. And so, in particular, about along a circle, right, because we have an arc length. So this is a distance divided by time. Now, I'd like to talk here real quick about the fare, because I think it gives a real good representation of the difference between these two. Linear velocity, let's start with the Ferris wheel. Let's consider a Ferris wheel. You don't feel like you're going very fast. It certainly has what would be a very low angular speed because you're not going through much of an angle very quickly, right? If they did, you'd all fall off the Ferris wheel because they don't even, you don't even have seatbelts on it. So it has very low angular velocity, but it could have a pretty decent sized linear velocity. You're still covering a pretty big distance on a Ferris wheel. The flip side of that is all the rides that are designed to make you, lose your fare food, right? To make you ill. They have a very high angular velocity, right? They tend to spin you around in circles really, really, really fast. Very small circles, really fast. So they have a very high angular velocity, but they might have a lower linear velocity. We have these formulas. You're going to want to work with them, and good luck. Thanks.